Alright, as we get started today, we're going to see this symbol here, which is an integral that has no limits on it. We call this an indefinite integral because it's not taking a definite area. It's not going to be a definite calculation. And so what this is going to mean is find the antiderivative of the integrand. So the antiderivative, or an antiderivative for f, is symbolized by capital F. And because there's many antiderivatives for f, we have to add the plus c. These are going to be the integrals we deal with today, but the same technique that we do today can be translated to definite integrals when we get there. I've shared this document with you because we, by virtue of knowing derivative rules, know already lots of integral rules. Because all we have to do is undo the rules we know for derivatives, and we have a whole bunch of integral rules. So for example, the integral of a constant is going to be constant times the variable plus c. Okay, in this document, all the variables are u's. Okay, we know how to undo the power rule. So the integral of a power function is to add 1 to the exponent, divide by the new exponent, add a plus c, and so on and so forth. Okay, so we know that we've seen secant squared u is the derivative of tangent u, so the integral of secant squared u would be tangent of u. So this is a list of about 15 or so rules that we know, and these are going to be called the common integrals of calculus because they're ones we know without having to do much work. What we're going to talk about today is when you are approached by an integral that is not on this list, one that's not so common, and how we can get around that and still be able to evaluate them. So the basic idea is that unless we have an integral that's on our list, in other words, it has a nice antiderivative, we need a new technique. So the technique is going to be to substitute variables and change the integral from one that's not so nice to one that we have on our list. The ground rules that we have to operate by are these. We can make any substitution we like as long as you substitute all the pieces out and have an integral that only has one variable. So I'm not going to have an integral that has u's and x's in it. This is still single variable calculus. So only one variable is allowed. And then I wrote this little statement here, we can multiply by 1. And that's actually going to be pretty important as we move forward. Multiplying by 1 is not going to change the value of our integral, but it can definitely change its appearance in a way that will be helpful for us. So let's jump right in. This is not an integral that is on my list. This is not a function that I know the antiderivative of just by looking at it. It's not a basic antiderivative. So we want to transform this integral into something that's on my list. I look at what I have presented to me in the integrand, and the closest thing that this resembles on the list would be integral e to the u du. So I'm going to try to transform it, if I can, into this. So if it's going to look like this eventually, that means that x squared has to be the same as u. So this is where the substitution begins. We get to choose, and it's not always obvious in the beginning what to choose, but we play around until we get it right. Let's let u be equal to x squared. Simple enough, we're going to make a substitution. But remember, I said you have to account for all these other pieces and not have other variables besides this variable u in your integral. And by the way, you don't have to use u as the variable to substitute, but that's just what's commonly done. All right, let's start with this dx. This needs to disappear, and if my variable is going to become u, then there's got to be a differential du in the problem. So where's that going to come from? Well, differentials are pieces of derivatives. So I'm going to take the derivative of both sides of this little equation that I came up with. So that would give me du dx, if I use differential notation, is equal to 2x. And if I solve this for du, treating the derivative du dx as a fraction, which we've been able to do in certain situations, then I'll have 2x dx. Now I got to look back at my original problem, and I have to ask myself, if I'm going to have a du, that means there has to be a 2x dx in the original problem. So I look back up here. Obviously I have the dx. I have an x, but I don't have this 2. Now luckily we can do a little bit of fudging here. Okay? I would love it if I could just place a 2 right in there. And the good news is I can. Because I can multiply by 2 on the inside and counteract that by multiplying by 1/2 on the outside. Because remember, constants can travel inside and outside of an integral. So really, what have I done here? I've multiplied this integral by 1, which doesn't do anything. Okay, so now the 2, the x, and the dx can be replaced by du in that integral, and the x squared can be replaced by u. So that gives me a new integral. Okay, I have 1/2 still out in front, and my new integral is e to the u. And if I group those other three terms together, I have du. This is now on my list. I know the antiderivative for e to the u. It's itself. The 1/2 comes along for the ride. So my antiderivative is 1/2 e to the u plus a constant. And now I'm going to convert back to my original variable, which was x. And so if u is x squared, then my antiderivative for the original problem is 1/2 e to the x squared plus c. I'm going to do this only one time, but point it out right now. You can always check your work if you're not sure if you're right. How do you do it? You take the derivative of your answer. So if I take the derivative of 1/2 e to the x squared plus c, what should I obtain when I'm done? If I've done it correctly, I should obtain the original problem, which was x e to the x squared. Okay, so let's see here. 1/2 times e to the x squared stays the same, and then I multiply that by the derivative of x squared because I use the chain rule. So times 2x, the c is a constant, so it gets wiped out, and the 2 and the 1/2 cancel out, and so what am I left with? X e to the x squared, and that's the original. So I'm not going to do that in the rest of the slides, but that's a good way to know that you're right when you do these type of problems. Okay, this is not on my list. I have a sine x dx on my list and a cosine x dx on my list, but not the product of those two. So I need to make a substitution, and it's my choice. So you don't always know what to make your u equal to, but the best thing to do is just to experiment and play around and see what happens. You may not get it right the first time. It's kind of like when you first learn to factor. Sometimes you do it more than once. So I'll choose to let u be sine x, and I need to create the differential du, so I'll take the derivative of both sides of that equation, and I'll get du dx equals cosine x, and solving for du, I'll get cosine x dx. I look at the original problem, and those two pieces have to be there. And luckily for me, they already are there. Nothing has to be manufactured here. So I can replace sine x with u and cosine x dx with du, and I have a new integral. Integral of u du, and I got to look at my list and see which pattern this matches. Okay, this is really u to the first, so this is a power function, and I just have to undo the power rule here, and that's easy to do. I add 1 to the exponent, and I divide by the new exponent. Add a plus c, and then I got to convert back to my original variable, which was x. So I go back and look and see what u was, replace it, and I'm finished. What was u originally? Sine x, and so there's my antiderivative. Okay. If you're curious, you might redo this problem a different way, letting u be equal to cosine x, and see if you get the same answer or not. All right, here we got a new, and again, it's not always obvious what to make your u, okay? But we got to look at our list of possible patterns. And one of the possible patterns on the list is, I'm not sure how it's written. It's either written as du over u or 1 over u times du, one or the other. I can't remember how I wrote it on the common integrals list, but this is going to be a common pattern that we see. In other words, the derivative of my u is in the top and my u is in the bottom. So if I see an integral pattern that kind of looks like that, then this is a good idea of what to make your u. So if I look at the denominator, x squared plus 1, its derivative is 2x, and I kind of have 2x in the numerator, something close to it. So I'm clued in here that perhaps I will be well off to make my u x squared plus 1. Du dx would be equal to 2x, and so my du that needs to eventually appear in this problem is going to be 2x dx. Now, remember, I need these pieces to be present. So I have the dx, I have an x, and I have a 4. But we could rewrite 4 if we wanted to as 2 times 2, correct? And I only want one of those 2's on the inside, so I can take one of them outside and have this integral right here, okay? 2 times, there's still a 2 on the inside, I still have an x and dx, so there's my du is in the numerator, and my u is in the denominator. Okay, this pattern du over u, or 1 over u du, however it was written, is a famous pattern for us. That's going to be the pattern for natural log, and so I have the natural log absolute value bars of u plus c. Remember that when we took the derivative of 1 over x, we needed absolute value bars to do the antiderivative. So we still need them here. Now we replace our u, and we're finished. So x squared plus 1 plus c. And it turns out that x squared plus 1 is always positive, so in this case we could have dropped the absolute value bars, but in general, hold on to them. All right, this one looks similar to the one we just did. And so perhaps I should do the same thing. I should let u equal x plus 1 and see where that takes me. Okay, if I do that, then I get du dx is equal to 1. And so du and dx are equal. And so that's great, because I have a dx. I can replace it with du. My denominator is u, but I still have a problem. Okay, at the moment, I still have a 4x in the numerator. Now, what can I do? I can certainly pull the 4 out front, but I can't pull the x out. Okay, variables don't travel inside and outside of integrals at all. So what do? I'm not allowed to have an integral that has x's and u's in it. Conveniently for me, there's a relationship that we created between x and u. It's up here. So I can solve this little equation for x, and that would allow me to get rid of this x and rewrite it in terms of u. So x would equal u minus 1. Okay, really neat. So what do I have now? I have 4 times the integral. X gets replaced by u minus 1 over u. Now, is this any better? Well, that's what we have to be able to recognize. I can split this as u over u minus 1 over u, which becomes 1 minus 1 over u. So that's 2 separate antiderivatives to do. I can do them together or split them up. But the first one becomes u, and the second one becomes the natural log absolute value of u plus c. The plus c can actually go inside or outside this parenthesis. It doesn't really matter, because 4 times c is still a constant. So I have 4u minus 4 natural log absolute value of u plus a constant. What was my original u? My original u was x plus 1. So I have 4 times the quantity x plus 1 minus 4 times the natural log. This time I have to keep the absolute value bars because x plus 1 could be negative, depending on the x values. And then I put a plus c at the end. Now, a couple warnings. It's going to be very tempting to do some things that look like they work. For example, you may be presented with integral of cosine squared x dx, and you say, hey, this is like a power function. And if it's something squared, then the antiderivative should be 1/3 times that thing cubed plus c. If we do a u sub, though, we'll notice that if u is cosine x, then the du dx would be negative sine x, which does not appear anywhere in the problem. So my teacher back in high school had an expression: no du, no can do. If your du does not show up in the original problem, you cannot do the integral that way. It's got to be done a different way.